The title for this project is Advanced Deep Learning for Medical Imaging, Pneumonia Prediction, and COVID-19 Detection. Our goal for this project was to develop a deep learning model capable of analyzing photos to classify individuals as having pneumonia, COVID-19, or being healthy. We will now introduce ourselves. My name is Fabiola Rivera Noriega, and I am the product owner and team lead.
I'm Eduardo Suarez.
Hi, I'm Danny Gutierrez.
My name is Ryan Pareda.
And I'm Justin Trewick.
Our motivation for this project stems from a deep passion for using advanced technology to improve healthcare outcomes, especially in underserved and impoverished regions. Diagnosing pneumonia and COVID-19 quickly and accurately is crucial, particularly in areas with limited access to medical resources and specialists. We acknowledge that sometimes diagnostic methods can be time-consuming and prone to error, especially under heavy workloads faced by healthcare professionals in such settings. By leveraging deep learning, we aim to provide a tool that can assist doctors in making faster, more reliable diagnoses, even in resource-constrained environments.
So for this project, we will explore the efficacy of deep learning through a convoluted neural network to be able to make diagnoses on certain medical images. Negative cases of COVID-19 that were gathered from a publicly available hospital repository in Sao Paulo, Brazil.
I'm sorry. I think you cut off for a second and it missed like a whole sentence.
Yeah, I got like a unstable internet connection message.
Oh, okay. Can you just do the PowerPoint again?
Yep. Okay. For this project, we will explore the efficacy of deep learning through a convoluted neural network to be able to make diagnoses on certain medical imagery. Model on includes patient CT scans of both positive and negative cases of COVID-19 that were gathered from a publicly available hospital repository in Sao Paulo, Brazil. COVID-19, a dangerous coronavirus that targets the respiratory system, itself needs no introduction, as it's public health, the economy, and education have all affected us in some way ever since its first outbreak in 2020. These scans, like the one shown on the right, where the top scan shows a positive test and the bottom one shows a negative test, are first converted into image sensors, which you can think of as multidimensional numerical arrays from which our model learned to identify critical visual indicators or features of COVID-19 and CT scans. These indicators can include hazy opacities, which visualize inflammation, dense white areas, which indicate fluid buildup, and particular lines, which suggest lung damage.
Pneumonia is a form of acute respiratory infection caused by viruses or bacteria, and it leads to mild to life-threatening illnesses in all ages. It is the largest infectious cause of death in children worldwide, killing over 808,000 children under 5 in 2017. These chest X-ray images were sourced from pediatric patients aged 1 to 5 years old at Guangzhou Women and Children's Medical Center. An example of these can be found to the right of the screen. These images were part of routine clinical care and they underwent quality control to exclude low-quality or unreadable scans. The diagnoses were initially graded by 2 expert physicians, and then they were validated by a 3rd expert to ensure accuracy. As for our project, we're going to train, test, and validate our model with X-ray scans from both pneumonia patients and healthy individuals. We'll convert these X-ray scans into image sensors, and our CNN model will use its feature classification layers to detect signs of pneumonia in the X-rays. Now, in the realm of medical imaging, deep learning has emerged as a transformative tool, offering unprecedented accuracy and efficiency in diagnosing various conditions. Researchers have developed deep learning algorithms capable of analyzing medical images such as X-rays, MRIs, and CT scans to detect diseases like cancer, pneumonia, and COVID-19. For example, AI models have been used to identify early signs of breast cancer in mammograms, predict the likelihood of heart disease from cardiac scans, and even detect neurological conditions from brain imaging. These advancements highlight the potential for deep learning to revolutionize diagnostics by providing faster and more accurate assessments, which is particularly beneficial in regions with limited access to medical professionals. Despite these promising developments, ongoing research is crucial to address challenges such as data privacy, model interpretability, and ensuring the robustness of AI systems in diverse clinical settings.
An artificial neural network is a machine learning model inspired by the way biological neural networks in the human brain process information. They're used in machine learning and AI to recognize patterns and make predictions based on data. A neural network is composed of neurons, which are the basic units that process input data, similar to biological neurons. It's also made up of 3 layers, as you can see on the right. We have the input, hidden, and output layers. The input layer takes the data, the hidden layers makes the computations, and then the output layer produces the final result. We have different types of neural networks, but for our project, we decided to use a convolutional neural network.
A convolutional neural network is structured in the way that a regular neural network is, as explained before, but with the inclusion of convolutional layers. These layers generate a filter of the image called the feature map by performing many convolution operations on it using matrices called kernels. During training, each kernel is made such that the feature map it generates represents a feature of the input to its layer that is relevant towards ultimately making an accurate prediction. A layer can have many kernels associated with it and thus represent many different features of its input through the feature maps they generate, which are then passed as input to deeper convolutional layers. These deeper layers will take all of the maps generated before it and use its own kernels to generate maps based on the entirety of information before. In this way, the layers can be thought of as progressively compressing information such that the feature maps will progressively represent higher level and abstract features like a head, a tooth, or water, or the ocean. The maps at the deepest layer are ultimately what informs the final layer of their values, making a prediction. Okay, so some models contain layers with pre-trained kernels that prove to be very successful at identifying features of images that are useful across a variety of ML tasks. These feature maps can serve to inform conclusions that are unrelated to the original purpose of the model. For example, a model can be trained to make classifications from 100 different classes and be repurposed to classify from just 12. Doing this requires the deeper end of the model to be extended or modified and then trained such that its output fits a new purpose, while the earlier convolution layers remain unchanged and provide the new layers with features. So 2 examples of feature extraction models are VGG16 and ResNet50, where VGG16 is a model with 16 layers and 3x3 convolutional filters, kernels, and ResNet50 is a deeper model with 50 layers and is generally more effective. We did use both of these models, but we found that ResNet50 performed better. Oh, okay. So here's a short description of the models that we used, VGG16 and ResNet50. We use them as backbone models to extract features, and the layers and activations were pre-trained. Well, the convolutional layers were pre-trained, I believe, on the ImageNet data set, and we used the PyTorch framework to modify the purpose such that it predicts positive COVID, negative COVID, positive pneumonia, or negative pneumonia. The training involves batch training, gradient resetting, loss computation, and optimization, which is essentially about updating the weights after a batch of training images are evaluated using a gradient, which essentially tells the weights how to approach a more optimal value, which minimizes the loss function, which is a function that tells the model, well, it generates a metric explaining how well the model is doing or how bad the model is doing. And then we evaluate the model using statistics statistical metrics like accuracy, F1 score, precision, and recall. F1 score typically being the most useful as a mean between precision and recall. And we were also able to customize these models using different hyperparameters such as activation value, activation functions, loss functions, batch size, etc. And we are able to train these on CPUs and GPUs, NVIDIA GPUs, but we chose GPUs as they're basically always more time effective.
And here are the results for our pneumonia dataset. So first, we have an accuracy of 0.94, which means that 94% of the predictions made by our model were correct. Now, accuracy gives us a general sense of how well the model is performing, but it doesn't tell us the whole story. Next, we have the F1 score, which is 0.96. Now, as you can recall, the F1 score is a balance between precision and recall. It's particularly useful when we want to ensure that both false positives and false negatives are minimized. A high F1 score indicates that our model is performing well in both of these aspects. Precision, which is 0.95, tells us about the accuracy of the positive predictions made by the model. In other words, 95% of the instances that our model predicted as pneumonia were actually pneumonia. High precision is crucial for minimizing false positives, which is important in medical diagnoses to avoid unnecessary treatments. Recall is 0.97, indicating that 97% of actual pneumonia cases were correctly identified by our model. High recall is essential to catch as many true cases as possible, ensuring timely medical intervention for those infected. Overall, these results show that our model is highly effective at diagnosing pneumonia, with excellent performance across all key metrics. This level of accuracy, precision, and recall means that our model can be a reliable tool for supporting healthcare professionals in identifying pneumonia cases, ultimately improving patient outcomes.
And here are the results for our COVID dataset. Our model achieved an accuracy of 0.90, meaning that 90% of our predictions, the predictions that it made were correct. The F1 score is 0.91, which balances precision and recall. Precision is 0.89, indicating that 89% of the instances predicted as COVID were actually COVID cases. Recall stands at 0.94, showing that 94% of actual COVID cases were correctly identified by our model. These results indicate that our model performs very well in identifying COVID cases with strong accuracy, F1 score, precision, and recall. This performance level demonstrates the model's potential to be a valuable tool in the healthcare sector, helping to diagnose COVID efficiently and accurately, thereby supporting better patient outcomes.
Our research into the application of convolutional neural networks and deep learning in medical imagery opens up a number of potential use cases in both academia and healthcare. Students and researchers can delve into a project to see how machine learning techniques can be applied to real-world medical data. By having access to our code base, documentation, and results, we hope that our research serves as a catalyst for individuals to continue innovating in the world of AI, regardless of the field of study. Furthermore, our research offers valuable insights for medical professionals seeking to leverage cutting-edge technologies in their practice. By showcasing the power of convolutional neural network models in analyzing complex medical images, we can inspire medical professionals to explore how AI can complement their expertise, leading to faster and more accurate diagnoses and ultimately improve patient care.
And that is all for our introduction. Thank you.